Okay, so this is, in a way, class meeting 9. So this is the only video that I'll be recording while I'm away. Um, so the purpose of today's class, if you will, is to get the ball rolling um, on assignment 3. I'm going to post the files for that after class. And also, so to help you get started with that, I'm going to present a code for a simple exercise. So what I showed you last time was denoising an image, um, and by solving the Peronomalek equation, a nonlinear PDE that's diffusive in character. So I'm going to just apply ordinary diffusion to an image and show you what that looks like, and acquaint you with basic tasks for handling images, um, and certain aspects of solving time-dependent PDEs, including spatial discretization, time stepping, etc. And in the third assignment, I know I haven't graded the first 2 assignments. Then again, most of you have not turned in the second one yet. I plan to grade the first one. In fact, not everyone has turned the first one in either, but most have. I will grade those very soon, like within the next day or two. Um, so what I show you in today's class, the idea is for you to build on that for assignment 3. So assignment 3 is basically the default final project, unless you want to do something else, which at least one of you has so far. Okay, so um, so what I have here, this file, diffuseimage.py, is I'm going to walk you through this. So the idea is I'm going to solve the two-dimensional heat equation. So dudt is equal to some positive constant c times the Laplacian of u, so uxx plus uyy. And the initial data is going to be read from an image. I will also impose, for simplicity, periodic boundary conditions. And because it's diffusive in character, this PDE, way the solution is going to behave is that um, the image will be diffused. It's going to essentially blur the image, because if I were to let this run long enough, I'm only going to run it for a short time span. But if I ran it for long enough, then it would the image would decay to 0, all the pixel values. Now, how rapidly it will diffuse depends on the value of a constant c. So I'm going to show you this for different values of c. So the larger the value of c, the more rapid the exponential decay of each Fourier component will be. The faster the pixel values will diffuse to 0. Um, now, let's see. Actually, sorry, I goofed here. I was thinking of the wrong boundary conditions. When it's Dirichlet boundary conditions, the solution, if allowed to run long enough, will diffuse to 0. It does, when it's periodic, it does not. What happens is whatever the mean value of the pixels are. So if the mean value of your initial data, um, that one component, the component in the direction of a constant function, um, does not experience any exponential decay because it's corresponding to a frequency 0, and the rate of decay is controlled by the frequency. So that constant component will remain. All others will diffuse to 0. So the solution will converge to a constant. So if I set dudt equal to 0, um, then that tells me what the steady state solution is. So when I have uxx plus uyy now equals 0, what kind of functions satisfy that? Well, certainly linear functions satisfy that. Linear in x and y, because their second derivatives with respect to x and y would be 0. But we also have to satisfy the periodic boundary conditions. So what kind of function satisfies that? It's a constant. Um, so uh, so the larger the value of c is, the more rapidly the pixel values will converge to that constant, which is the average. Okay, so how do we proceed? So I have, sorry, Haley, I'm using your image again. So I have this image in a file. It's a pretty small image, like 100 something by 100 something pixels, just so the computation won't take forever. And I use image.open from the PIL package. So I need to import this um, package from PIL and then use its open function to read the image into this structure A. So this is a complicated structure that has a lot of members, which we only need a few of them in this. So I won't really get into that structure here. This is something you can always look up to find out more about the information that is stored in A. Certainly we need the dimensions of the image. So A.height, A.width give us the dimensions in terms of pixels. And then we want to represent the image as a three-dimensional array. That would be m by n by 3, the 3 corresponding to the 3 channels, the RGB channels. So the way we get the image in that form, so when you read an image in MATLAB, there's imRead, and that gives you this three-dimensional array right off the bat. In Python, there's an extra step that's right here. So what I do is call the getData member function of A, and then I pass that to list. That converts it to a list. So this gives me all the pixel values, but I want that in the form of an ND array. And so I use the usual array creation mechanism to do that, but I also make sure that it's a float. So then what I can do is get that to so get this in the right form. So AMAT is that three-dimensional array that I want. So it's size m by n by 3. Now I have 3 channels, and I just want to work with one of them for this example. And that would be, so in order to get that, I want all values corresponding to the lowest index in the third dimension that corresponds to the RGB channels. So I just have colon, comma, 0. So that will give me everything in the red channel. So the channels are ordered red, green, and blue, RGB. So I fetch that one slice. And but this, in this form, however, is not as a matrix. It's actually as a vector of length mn. If I want to display the image, I need it to be as a matrix. So what I do is, after I get this slice for the red channel as a vector, now I reshape it into an m by n matrix. Now for a computation, so when you're solving numerical PDEs in higher dimension, generally you want those in the form of a vector, which is what I have right here. I'm only changing it to a matrix for display purposes. So what I do here is go ahead and reshape it, and now I have the red channel of the image as a m by n matrix. Okay, so now just go ahead and display that. So I can use, we've used the matplotlib functionality before, but instead of using a plot function, I use its function imShow, image show, and in order to not get freaky colors for this grayscale image, because a single channel of a color image is a grayscale image, I use cmap equal gray, and that will cause it to be displayed in grayscale. There are other color maps, so the default color map is not gray, as I found out the hard way. And then I can call show to actually display that. So now I see what the original image is, and then I go ahead and make this into a vector for time-saving purposes. And I want to be careful about the order, which is why I didn't just stick with this. I want to know what order that I'm dealing with. So I use the Fortran order, and basically I could work either way, but I'm accustomed to the MATLAB ordering, which uses a Fortran convention, where matrices are stored in column major order. So first column, then second column, and so forth. As opposed to the C ordering that is row major order. Okay, so now I have a vector in the so now I have this channel stored as a vector in the a known ordering convention, so I can work with it for time stepping purposes. I'll choose a delta t of just 0.1 and a final time of 1. These are pretty arbitrary choices here. I'm going to use backward Euler for time stepping. That way I don't have to worry about stability. So I really could have chosen any and any time step that I want. Okay. All right. Now, okay. So now we have. So now that I have my time stepping parameters, I go ahead and choose the number of steps, and then we have. I need to make my spatial differentiation operators, one for computing uxx and one for computing uyy. This is finite differences. So for that purpose, I'm going to need identity matrices of size m and n, because as I explained in the last class, I use a Kronecker product to build higher dimensional partial differentiation matrices. If I have my dx and the dy's, so we're thinking of in terms of solving this equation on the domain 0 to 1, 0 to 1, in both x and y. So therefore my spacing would be 1 over m for okay, is this even? Oh, you know what? Okay. This is gonna drive me crazy. Okay. M corresponds to height of the images for rows, so that should be n and m. Okay. All right. So because we have a m row by n column matrix, so now I'm thinking, oh gee, what else is going to be? All right. Okay. I'm hoping it doesn't throw things off too much, but it's going to be interesting because I just ran this code before I started this video. It may end up just being a scaling issue, nothing more. I believe the image is not exactly square, but close to it because I was just cropping part of the original image. Okay. Well, we'll see when I run it, but I don't want to do that yet. Okay, so this is my spacing dx and dy. Now, because remember, m is height and n is width, so that's why the spacing has to be this. So now for a one-dimensional second derivative matrix, I use the center difference. I'll fill it in here. Ux at a certain point xj is equal to uj plus 1 minus 2uj plus uj minus 1 over dx squared. So the coefficients are 1, minus 2, and 1. So minus 2 is on the diagonal, 1's above and below. So I make this tridiagonal matrix with these coefficients. And I put them on the subdiagonal, main diagonal, superdiagonal. So then we have, so now sp.x, I've shown you this before. This makes that one-dimensional second derivative matrix and second order accurate. I use CSR here because I need to modify entries after this, which I can't do by the default format, which would be DIA format. It wouldn't let me change individual entries. So now I need, for periodic boundary conditions, I need wraparound. So I need, so matrix has to have this structure. I'll make a multi-line comment here. So we have minus 2, 1, 0. Well, first I'll fill in the default form where you just have Dirichlet boundary conditions, where you just only have the diagonals. Okay. Okay, need more spacing here. Okay. All right, and then So I need to go all the way down to the bottom. Okay, so minus 1, 2, sorry, 1, minus 2, 1, minus 1, and then minus 2. Okay, so this is what we have just from diags. But then what I do is I need the super and subdiagonals to wrap around. So like these ones on the super diagonal have to wrap around and and I need a 1 down here. And then similarly, the subdiagonal goes down here, wraps around up here. This is a periodicity coming into play. So for instance, j equals 1, I have ux of x1 is equal to u2 minus 2u1 plus u0 over dx squared. And then, actually, I'm numbering the points from 0 to, I have n points. My grid would be x0 equals 0, x1, x2, xn, and then xn plus 1. So n is the total number of grid points, which would be either little m or little n, depending on which variable I'm in, equals 1. So only these points, sorry, xn minus 1, xn. I have n points I'm actually using, x0 up to xn minus 1. This one is not included in the grid because of periodicity. So if I look at the second derivative of x0, I'll have u2 minus 2u0 plus u sub minus 1, but that's not in my grid either. I need to wrap around, so it'll be un minus 1. So I have, okay. So I have there's a super diagonal entry, there's a diagonal entry, and then I would have a subdiagonal entry, but because of wraparound, I end up with a 1 out here. And then at j equals n minus 1, so the upper boundary, or near the right boundary, equals un minus 2 un minus 1 plus un minus 2 over dx squared. And so these 2 points are included in my grid. So that leads to the coefficients of 1 and minus 2 out here. But un is not in the grid. I'm not including it. So I have u0 by periodicity, and that's why we have a 1 in the first position over here. So that's what I'm handling down here. I'm adding these entries. Now, so for instance, here I want an entry in the first row, last column. And that's where the Python's convenient negative indexing comes into play. Minus 1 refers to the last. So it's kind of like using end as an index in MATLAB. And I go ahead and fill that in. And then here I want the first column, last row. And I fill in that corner entry. And I do the same thing for differentiation in respect to x. Same deal, except it's using dx instead of dy, and using n instead of m. Okay. Now, those are my one-dimensional differentiation matrices. And when I take Kronecker products with identity to get the partial second derivative matrices. So here, this is for computing uxx. So identity is the second operand of a Kronecker product, and then for uyy, it's the first operand. So then I can add these 2 matrices together, and that is my matrix that computes finite difference approximation of the Laplacian of u. So now I'm ready to do my time stepping. So I start with t equals 0. I take this number of time steps that I determined earlier, and I'm going to use min-res. So for backward Euler, I have un plus 1 is equal to un plus delta t times c times Laplacian times un plus 1. Un plus 1 is my unknown. So if I rearrange this, I get identity minus delta t c Laplacian un plus 1 is equal to un. So I'm solving a system of linear equations every step for backward Euler. I'm going to solve it using min-res. This is a symmetric matrix. It's actually positive definite. So I could use conjugate gradient, but I don't feel like dealing with preconditioning. So I'm just going to use min-res instead. And for our purposes, this is a good method, at least for a small image like this. But I'm not going to, so what I'm going to do is, even though I built a Laplacian matrix, I'm not going to build the whole matrix identity minus delta t times Laplacian explicitly. Because I want to show you another way of working with matrices. With Krylov subspace iterative methods such as min-res, also conjugate gradient, GM-res, biconjugate gradient, etc., they only work with, the matrix only manifests itself through matrix vector products. So you could have a different way of computing a matrix vector product. Instead of forming a matrix explicitly, maybe you have a function that accepts x as input and returns the product a times x. As long as you have that, it doesn't matter how it's done under the hood, then you can use that with an iterative method. And the Python iterative method functions, as well as the ones in MATLAB, accommodate this. So I create a function using my Laplacian matrix and the value of c and the value of dt to define a function on the fly. F takes an input x and returns the matrix vector product, identity minus delta t times c times Laplacian, all times x. So f is my function that does a matrix vector product. So now I define a linear operator. This is in the scipy.sparse.linalg package, which I've imported as FPL. And I define a linear operator that's size mn by mn, because that's the size of a matrix. And I define its parameter matvec to be equal to f. And what a linear operator does is you give it a vector x, and it'll return. Use this function f, defined here, to return the matrix vector product ax. Okay, and now I pass a, my linear operator, to min-res. That's also in the scipy.sparse.linalg package, along with other iterative methods, and you can look them up there. So a is my linear operator, u is my right-hand side, the solution for a previous time step, and I'm also going to use that as the initial guess. This matrix is a perturbation of identity, especially if delta t is small. This matrix is already close to identity, so un is already close to un plus 1, so it makes sense to use it as an initial guess. Might save you some iterations. Now you don't have specified initial guess. If you don't specify one, then the default is to be the zero vector. But we have enough information to do better in this case, so why not? And the default tolerance is 10 to the minus 5, but I'm filling it in anyway because I'm going to change it later. This function has the iteration stop when the relative residual norm, because remember, residual is b minus ax. So the relative residual norm is the norm of that divided by the norm of b. Once that is sufficiently small, then the iteration stops. However, it's worth keeping in mind, like, of course, when you solve ax equals b, then b minus ax, the residual, ought to be 0. But as worked out in a class such as 610, and I'll refresh this here. So r is equal to b minus ax, and I'm gonna let x star, actually x tilde, x star, refer to the exact solution. So then the error is equal to x star x minus, okay, yeah, x star minus x. So now suppose I multiply e by a on the left. ae is equal to ax star minus ax. Well, ax star is equal to b because x star is the exact solution. So now we have a relationship between the residual and the error. A times the error equals the residual. Now, if I take norms of this, so if I rearrange this first, e is equal to a inverse times r. Now I take the norm of both sides, and the norm of the product is less than or equal to the product of the norms. And I want to do relative error. So I'm going to divide this by norm of x. And, okay. Now, the next thing I'll do is I'm going to multiply and divide by the norm of a. Now, the norm of a, so the norm of a times the norm of x is greater than or equal to the norm of, actually, it needs to be x star. The norm of a times the norm of x star is greater than or equal to the norm of ax star, which is b. But this is the denominator, so I can therefore say, I can replace the denominator with the norm of b, and still maintain this less than or equal to relationship. So this means it's a relative error is less than or equal to norm of a times norm of a inverse, which is a condition number, times the norm of a relative residual. So in other words, the residual could be small, and the error could still be large, because if the matrix is still conditioned. And matrices that come from spatial discretization of PDEs to get systems of ODEs, they are always ill conditioned. So just because the normal residual is small doesn't mean that the error is going to be small. Something to keep in mind. Okay. Once I get my solution back from MinRes, one thing I'm going to do is I'm going to compute the infinity norm of a solution and show it every time step, just so we can see how it behaves from one time step to the next. So we'll print that out. And then I reshape into a matrix just for display purposes so we can see the progress and show the image, and then keep the time stepping loop going. Okay, so now I'm going to go ahead and run this. Okay, so I need to import that. And I'm going to start with a pretty small value. I'm hoping that when I saw that mistake earlier, dx and dy, that now things aren't hopelessly screwed up. Let's see what happens. Okay, so here it shows the image, and then first time step, not much happened. And what we see is very little happening. Although notice, look at the norm of a solution, 209, 205, 201. It's gradually decreasing. And this is expected because when it's showing an image, all the pixel values are decreasing because the solution is diffusing to a constant, but for display purposes, it doesn't really take it into account. That's why the image doesn't appear to be changing very much. Now I'm going to choose and because it's 0.001, that means there's not much diffusion going on. So let's choose something much larger, so 0.1. And see, it got very blurry. And it's still decreasing. But yes, so what's happening here is the larger the value of C, the more rapidly, the blurrier the image gets. Okay, so I choose something between like 0.01. It's kind of in between in terms of a level of blurriness. Okay, all right. So that's the behavior that we have. Now, the Proto-Malik equation does, whereas this equation does, the heat equation does all forward diffusion. Proto-Malik does selective forward or backward diffusion, depending on how the gradient of the image is behaving. And that's why you get noise removal or smoothing in some parts, and then backward diffusion or sharpening in other parts, depending on how you choose the parameters. So you have to be careful about that. Okay. So one thing I just realized, and I didn't realize until I started making this video, is I've shown you how to load an image from a file. Never did show you how to save one. And I'm embarrassed to say it because I didn't bother looking that part up. I was only concerned about how to read it. And this is not a great solution here to just try to I could just go ahead and save this image. Um, so as far as documentation on the packages, the image package in uh, PIL. Um, so okay. Okay, and so here we see that this kind of example here again how we open an image from a file. What as far as format goes, I had previously saved the image in .png, and things got all screwed up when I loaded it. I recommend working with JPEGs for this assignment because what happens is like there's something about the data, it just doesn't display correctly. I haven't been able to sort out why just yet, unfortunately. So here we have a functionality for reading an image from a file, um, and um, okay. Hmm. I would hope that they also have a way to write an image uh, to a file. Okay. Um, okay, so we do have this. And unfortunately, they don't give um, examples. Um, but um, so what you can do is the first argument is FP, um, and so that'll be a string file name. And so the default usage is just to only specify that. It'll figure out the extension from a file name if you don't specify format. So I'm going to go ahead and try this. Okay, so I need to. Okay, so here's where I'm working in my file. So I'm going to take the. I'm going to run this again, and after time stepping, although what I need to do is um, I've messed with the data here, and I need to update that data with what I've just done. Um, and because right now I don't have a way of doing that. Okay. Yeah, because recall I used the get data function, um, this function here, to get the uh, pixel values. So this is what I did to get as an ordinary sequence. Um, and so now what I need to do is be able to, now that I've blurred it, I need to uh, go ahead and put it back. Ah, here we go. So we have so copying pixel data um, to this image, and um, okay. So what I'm going to try to do here is okay. Okay. Um, okay. So it needs to be a sequence. So yes, I'm just figuring this out right now because I didn't think of doing it earlier. This is what I get for trying to do things um, on the fly. And um, so what I could do is when I opened the image, it gave me an image object. So that's what I'm going to work with. Um, so okay. So after time stepping is complete, A is my image, and what I need to do is put data, and my solution is U, and it expects the data as a sequence. So if I so I could try that to put it as a list, and then save it. I'll save it in a different file name, of course. Okay. I have no idea. I actually have no reason to believe that this is going to work, but I'm going to try it anyway. Okay, so it's done some blurring. Let's get through the time steps. Okay, yeah, I didn't think it would. Oh, put data. Yeah, that is the right uh, method. Um, yeah, because A. Oh, that's why I reused A. So I'm going to change this A op and use that down here. Okay, so that was just reusing a name. So let's try this again. Okay, still didn't like it. New style get format per argument is not a tuple. Okay, so yeah, because I need to get this in. Oh, um, and it may not like it because it's not a color. Well, the other thing is, I need to be the matrix, not the. Otherwise, there's no way of figuring out the width and height. Sequence size image from the corner. Well, the new image is this updated image is the same size as the old one. Okay. Um, okay. And what it said was okay. So actually, I think I still want you. Okay. So unfortunately, I may not be able to do this now. Um, after all. Okay. Yeah. Okay. So I know what functions involved anyway, but as far as getting the data in the right format, I may have to. It looks like what I'll probably do is um, come back to come back to this later. Unfortunately, sorry about that. So yeah, certainly that's what I wanted to do is save your images into the right format when you're done. Okay. Um, and what I probably need to do is, it's unfortunate that there aren't examples um, in this case. Okay. Mm, well, let's go for broke here. Python save image from matrix. Ah, someone has asked this question. Um, okay, now here we give another way of doing it um, as a PNG file. Okay, I prefer using PIL because that's what I've been using so far. So um, okay. Um, oh, okay. Ah, okay. From array. Okay, I want to see if that is listed in the files, or sorry, in the commands. Ah, okay. Is there a to array also? No, there's not. That's interesting. Okay, so, all right, let's just try that then. Okay, so is image dot from array, and I'll use I think it was one for matrix. Otherwise, there's no sense of width and height. So I'm going to use umat, um, and then new image dot save. Okay. Now write mode F. Okay. Oh. I'm not sure if mode F would refer to Fortran as in storage convention or F as in float. And I'm going to see what that means. Cannot write mode F as JPEG. Yeah. This is how Python is picked up, isn't it? Basically spending all your time on Stack Overflow. Okay. And you could try converting it because it is a grayscale image. And okay, let's see if that'll take it. Okay. Oh, I need to save it as that. It doesn't convert doesn't update in place. How many more times am I gonna need to run this? Okay, no error. Now let's look in my folder here. Okay, we're done. So all's well that ends well, I guess. Okay, so this is okay, and now the other thing that'd be interesting is what if I could, like, I took one channel and worked with that and then saved only that, which is why this resolves a grayscale image. But I originally had a color image. So what if I could take this image and just basically stuff it back into that channel? So because I have an array already, and okay, so this is the original data. So let's see if I can work with that. Well, I want to print out its shape. Okay. Yeah, it's all as a vector. This is the 23309 is the number of uh, total pixels in a slice. Okay, um, and so width times height. Okay, so because honestly, I'm skeptical as to whether if I just go ahead and store this, it would that it would know what to do with the data. So okay, so what I'm going to try doing here is all right. So AMAT has everything. AMAT. I'm going to reshape it. MN3. So that was the original. And then AMAT, all rows, all columns, slice. So channel 0 would be the matrix that I have, UMAT. And then I want to do the same thing as I did before. Okay. And convert that. And I want to put a different file name. So the green and blue channels, okay, let's get through all this. The blue and green channels will be untouched. The red channel will be blurred. Okay, it doesn't like that. Okay, cannot handle this data type. Okay, so, because that is definitely an array. Okay. Yeah. If I go back from array, object with an array interface, that seems to be fine with a matrix, but not a uh, but not something like if I do this a map dot shape and print that out. Okay. Okay. Yeah, 143, 163 by 3. Um, okay. That that doesn't seem to know what to do with that. That it's like it's only for grayscale or something. Um, yeah. So I guess someone's tried to do this from color. So this is the same situation that's come up. Come on. Look how when you click on something and it like it thinks you're kidding. Okay. Um, and I don't know if it might have to do with the fact that there are different types. Um, because by default, pixel values are from 0 to 255. Those are 8-bit unsigned integers. But here I converted to floats. So what I'm going to do is, when I store this, I'm going to convert this to, um, it's not liking that. Oh, numpy dot, okay. That way, the whole thing is kept as integers. Yeah, it still doesn't know what to do with that. Okay. Um, now, actually, when I got AMAT in the first place, it was, okay. Yeah, it was all floats. Okay. Oh, okay. That seemed to work. So if I made sure these were floats, if I make everything int, take my solution, convert that also, so everything here is unsigned int. Now, as far as what we get, okay, now we have this. Let's see what we got here. Ah, there's Haley in color. Now, I want to open up the original. That's this one. Okay, and so 3 is the original, and 5 is the saved. Because there was some diffusion going on, so that's why the hue is somewhat changed. The feature is not so much. So what's happening is the red component is smoothed out, the blue and green components stay the same. So okay, so now we know how to save. So you found out at the same time as me how to save both grayscale and color images with a lot of experimentation. Okay, well, that was fun. Okay, so um, so as far as what I have in mind for the third assignment, so I'll post that file, and then I'll also post this one. So a lot of instructions. So the idea is you're going to write. There are 3 functions altogether. So the first one, oh, actually, I need to change the interface of this one. Okay. Oh, that's right. I had changed it in my solution. Okay. Um, all right. I have to move this further down. Okay. So what I was showing you earlier about using a function to define a matrix vector product. So I need to implement your own min-res from that. Um, okay, so we have, um, so as part of time stepping, you'll be defining some matrix A and you'll be solving this system of equations. So this is your right-hand side, which is coming in as U. So that's your right-hand side. It'll also be your initial guess. So it's specialized, it's not a very generic min-res, it's specialized for this purpose of time stepping. And the output will be your un plus 1. That's what gets returned uh, by this function. So a matrix is defined this way, and all this is defined here, but I'm going to move this. Um, okay. So A times X, the matrix vector product, is defined by a lambda function f of x. Like I showed you in the example, it'll be somewhat more involved matrix. Described here, identity minus delta t times forward difference with respect to x, coefficient g, which is a diagonal matrix, backward difference with respect to x, and then plus forward difference with respect to y times g coefficient times backward difference with respect to y. And so within square brackets, it's a matrix, and it's all multiplied by x. Now, I'm going to move this down to where the matrix would actually be made. Okay. Um, okay. Um, okay. So now, um, so as far as implementing MinRes, I've given you some things to go on. MinRes, the algorithm, is actually not explicitly stated in the text. I need to, which I thought I had open. Um, all right, iterative methods. Let's make this a little bigger. Okay, so we have GMRes, which is generalized minimum residual method for unsymmetric matrices, and we're using MinRes for symmetric case. So it's similar to this algorithm, but MinRes is based on the Arnoldi iteration, whereas so GMRes is based on Arnoldi iteration, which is right here. MinRes is based on Lanczos iteration, and I do have an algorithm for that. Um, algorithm 522. Okay, so that's right here. So it actually probably be best to go off of this. The difference is in how xk is computed. That is going to be done a little differently to solve a least squares problem rather than a square system. Um, and so actually, the least squares problem turns out to be more effective generally. And all of this is described here in the notes. So you can proceed either way using bits and pieces of either of these algorithms. So how you handle computing the solution from one iteration to the next is basically how you do it in algorithm 531, GMRes. But the rest of the code is going to be essentially Lanczos. Um, okay, so this is probably your best bet, following what's done in this paragraph right here to implement your own MinRes. And what I would suggest is once you have implemented, you can try this out on a generic AX equals B problem. You just make one up for which you know the solution, and see if and try it out and see if it works before you try it on for image processing. Um, Okay, so the U that comes in, again, serves as the right-hand side and the initial guess. That's just an artifact of the time stepping that we're doing here. Um, okay, and actually this... All right, this no longer applies. Okay. Um, okay. This... Okay. And in your codes, set a maximum number of iterations so that doesn't go on forever. Um, and then, um, okay, the uh, what I would suggest for a stopping condition is now the built-in Python function, like I said, uses a relative normal residual, which you could do as well. Alternatively, um, I actually don't like this stopping condition. What's interesting about this is if you look at GMRes, GMRes, go back to that. GMRes for general AX equals B, well, A square, um, performs this iteration and generates a um, Hessenberg matrix that's of J plus 1 rows and J columns. So it's slightly rectangular. And this last subdiagonal entry, um, if it were to become 0, then you'd actually have a way to get the exact solution. So the iteration proceeds as long as it's non-zero. And it's always going to be non-negative because it's a norm of a vector. It cannot ever be negative. So what's interesting is this is the algorithm described this way in Golub and Van Loan. As long as this subdiagonal entry is non-zero, proceed. And it also says in Golub and Van Loan, this is also the latest edition, but the final edition, 4th edition, that this entry is equal to the norm of a residual, B minus AX. That's actually a false statement. I found that I was skeptical about it, attempted to prove it, could not, and then I thought, well, let's just check it out. Print out both of them. They do not agree. So yes, I found a mistake in Golub and Van Loan. So I would actually this could still be used as a convergence criterion, although I'm actually rethinking it. Maybe something else would be a better idea. So I'm going to recommend. Okay. Same as scipy.sparse dot linalge.minres. Norm of relative residual less than a tolerance. What I mean by that is B minus AX, or norm of B minus AX over norm of B. Now in this case, A defines your function, and B is your right-hand side, which is actually U, the U that's being passed in. So use that less than some tolerance. Don't choose something really small like 10 to the minus 15, because due to round-off error alone, it'll never get there. Something like 10 to the minus 8. That's actually one thing I meant to show you when I was demonstrating its code. I had the tolerance at 10 to the minus 5th. If I were to run this at tolerance 10 to the minus 8th, I'd actually visibly see a difference. And that's why I'd recommend choosing a smaller tolerance than the default 10 to the minus 5th. I think 10 to the minus 8, 10 to the minus 10 seems to work well, based on just experimenting in here. But yeah, it's quite interesting how that significantly impacted the what we see here in the images. Okay, that reminds me. How long has this video been going on? Oh, I can't tell. I don't want to stop it either. I want to do this all in one shot. Okay, so All right, actually, I'm going to get rid of this comment because if we could use a Lanczos algorithm, um, as you see, I have a lot of comments in here already, then it becomes moot. So here's some details about the Python. For dot products, use uh, NumPy's dot routine. That's also good for matrix vector multiplication, but you can also use star for that. Now, the matrix that you're forming, your Hessenberg matrix, which is really a tridiagonal matrix because of the symmetry, it grows over time. And it's not as easy to add new rows or columns. Now, I showed you H-stack and V-stack before. That's for adding whole matrices. You can use that. And I found that if you're adding rows and columns to just a single row or column at a time, using append works well. And so using NumPy's append function, and you specify parameter axis equals 0 to add a row or axis equals 1 to add a column. But make sure it's a two-dimensional array. For instance, a row vector, if you're adding a new row, it has to be a 2D array, one row and however many columns. And similar for adding a column. Otherwise, it won't take it. Minres, each iteration involves solving a least squares problem. So use NumPy's least squares function. I demonstrated this in the last class, so you can use that example to get an idea of how to use that. So this is your minres. And then for denoising, so the setup is similar to what I've just shown you in the case of ordinary diffusion. A lot of it's repeated here, but you can just use the code that I just showed you in the diffuse image.py as a starting point. Okay. And one thing that I'd like to have you do, though, is because there's diffusion, like it's showed you here, the pixel values are decreasing, at each time step, rescale the image. So if you look at the whatever the smallest and largest pixel values are, and then rescale to map them to the original interval that they're in, which will almost certainly be 0 to 255. That's the maximum possible range. Just so we don't have all the colors converging to the same value. Okay. Now, so what you do is read the image, show the original image, and then as far as adding noise, if you generate, if you use numpy.random.randn instead of just plain rand, that gives you random numbers that are normally distributed rather than uniformly distributed. Scale them, because these will be between 0 and 1. But so scale them by a certain amount just so you can see the noise. You can see the fuzziness in the image. Like I multiplied them by 10. That seemed to work well. Okay, I'll put that in here. For example, 10. So I played around with different values. Okay, this is similar to what I've shown you in the previous code. And then your parameters, besides time-stepping parameters, the parameter k for edge detection. Because for a Perono-Malik equation, and actually, I want to make sure I made a note of that. Okay, exercise 11 in chapter 14. I'm going to update the book for you. I'll send that when I send other things. Okay, it's chapter 14. Okay, whoops, I went too far. Okay, exercise 11. Yeah, this is a Perono-Malik equation. So you need to choose that parameter k squared. When I played around with this for you before, I tried different values of k. Like larger values of k would cause very little change in the image. Values of k that are too small would cause massive blurring. You choose something in between and you get some actual enhancement of the noisy image. Okay. Okay. So you now that's actually passed as a parameter k. All right. The time-stepping loop is similar to what I've shown you in the other code. Here you're creating differentiation matrices like in the other code, but for first derivative only, using forward, backward, or center difference, all three of those. And then you can use those to put together um, the matrix that represents your entire differential operator. Do a wraparound for periodicity, like I just showed you. And then Kronecker product at 2D, like I showed you. In your time-stepping loop, here's your coefficient. For V's derivatives, du dx, du dy, use the center difference. Again, first derivative, not second. It's just ux and uy. And you have to do this every time step. The coefficient is changing every time step because the image is changing every time step. Here's your matrix. So you can define a lambda function like in the other code using your difference operators. When you have your coefficient g defined on the whole space, this is a vector, so it's defined on the whole image, but it's shaped as a vector because u is also a vector, and ux and ui will be vectors. So you put it on the diagonal of a matrix, and then okay, and then here are the difference operators that you'll need. So derivatives with respect to x, forward difference, backward difference, and then with respect to y, forward difference, backward difference. Okay, it'd be a good idea to try SciPy's min-res. Make sure things work well then before trying your own. So that way you're breaking it down into like getting one thing to work and the other thing to work. Okay, and then yeah, this is talk about remapping the pixel values from back to 0 to 255. Then reshape into a matrix for display. This is done in the other code. Then at the end, show the original image, the noisy image, and then the final image that happens after time step. Hopefully, it's a more higher quality image than the noisy one. So that's what you want to watch out for. That's how you can tell that your code is working, and then you've chosen good parameters. And then finally, using a different model for denoising. So I co-authored a paper 5 years ago. Okay, this one with Patrick Godati and Yoon Ho Kim. He's at UC Irvine. Kim was a postdoc at UC Irvine. So we developed a new model, a different PDE that does forward, backward, forward diffusion. So it does forward diffusion for really small or really large gradients of U, and then for moderate size gradients, it does backward diffusion or sharpening. It seems to work better than our previous model. So this is a paper for Godati, Kim, and Lambers. So you can go ahead and open it up. And the equation, and I've indicated this here in the notes, equation 1.3 at the beginning of the paper, just on the second page. Oh, wow. 1.2. That's it. Well, I'm having an update. This PDE, which is, except here, this coefficient is the same as pronomalic, except it's missing the k squared. I want you to include the k squared, just so we have more control over the behavior. But then we have, so everything in these parentheses, this parenthesis and this one, is the coefficient, which I've been referring to as g. So really, all that's changing is g. Otherwise, things are exactly the same. And you have new parameters. You have delta, and then parameter p. And p should actually be between, like, so the recommended value of p is like something slightly greater than 1, like 1.05. But what you should do, though, is once you compute the norm of a gradient of u, have a loop go through the array, and I'm going to make a note of this here. Computing the norm of a gradient, which is equal to square root of ux squared plus uy squared. So you know how to compute ux and uy from the other function, squaring them is no problem, and use like math.square root, but vectorized, because ux and uy are vectors. So take a square root of this whole thing. Iterate through the resulting array and set any 0 values to something small. Because if we choose p to be slightly greater than 1,
then we're going to have a negative exponent here, and we're in danger of dividing by 0. So once I fix that in my code to uh, set it to some small value that's still positive, then things work well after that. Okay, but generally it's going to work the same as your other denoising function. You just have these extra parameters, p and d for delta, to specify. Delta is something that needs to be positive. It's something you can play with. So if you set it to 0, then it just goes back to pronomallic. So once you get all of this working, then what I'd like you to do is find a way to write these two functions in such a way that they do not duplicate code. Because if you just do these independently, they'll look almost exactly the same. That's redundant code. So this may involve writing a function that both of them use, for example. So in other words, go ahead and get these working independently, even if it means you're doing a lot of copy and paste from the first one to the second one, and then and then go through it and basically redesign. This is a common task in software development, is that you design it a certain way, but then as needs change, functionality changes, you find you need to change that design, which can actually be really nerve-wracking because what if you break something, which actually I've done in the past. So something has to be done very carefully, but it's also something that's worth doing. If it results in a package that is more efficient or more robust or easier to maintain, all of these things. So that's something I'd like you to try doing after you get things correct. Now can you write the code in a better way where you're avoiding duplication of code between functions. Okay, so what I'm going to do is I'm going to post this file, pronomallic.py, and also diffuse_image.py. And I will grade assignment 1 soon. And certainly we can talk when I'm back for our next class on Tuesday, July 17th. We can talk about this, make sure that everybody's going. Certainly there's a more challenging assignment, and there's a lot of material here that I've just gone over. So we'll clean that mess up. So I will see, well, at least some of you on Tuesday. I still haven't got many submissions on assignment 2, so I'm hoping that everybody can at least finish that soon. So until Tuesday.